Hello, thank you for being here. So we are working in a French company that is called Teads. We work in the AdTech industry. You will understand a little bit later what we do exactly, but we don't show ads directly, and we don't have any website neither to publish the ads. We are in the middle. And with Anne, we are working in the same team. In the advertiser side of the ad industry. So me, I'm working as a data scientist, and Anne as a machine learning software engineer. Okay, so the first part of the presentation, during the first part, I will present the AdTech industry from a high perspective to explain you what kind of machine learning we need to use and to introduce what Anne will describe and to justify the stack that we'll put in place. So first, as a reminder, so maybe you already know what an ad on internet looks like, but we have mainly 4 kinds of ads. This one is an example of what we call search and performance. So search, why? It's because it's an ad that appears when you are searching for something. Here it's on Google, for example. So you are searching for a knife, and we will display you an ad about knives. So this is called search. And performance, it's because, as you can see here, we have displayed very specific products, like specific knives from specific sellers, because the advertiser wants you to buy the knives. So it's called performance because it's easy to measure the performance of this kind of ads, because we will see after if you bought or not the products that we showed you. Okay. Another kind of ad is what we call simple display or simple video, and for branding. So simple display or video, it's not inside a search engine, it's just inside a regular web page, as you can see here. So you are browsing the internet, you are reading some newspaper, for example, and you can see ads inside it. So it's the opposite of search. And here it's branding, because we are not displaying a specific product, we are displaying a brand. So we want you to know this brand, or to know it better, or to have it in your mind. So it's harder to measure a performance KPI for this, because how do you want to measure that you really have this brand in your mind? It's more complicated. Okay, so this was 2 examples. Of course, you can have search and branding, and video and performance, or display and performance. So you have like 4 combinations of possibilities. So how does it work in practice? So the first step is the user is browsing the internet. This will say if you are in a search or display context. So if the user is browsing on a search engine, it will be a search. Otherwise, it will be a display or video context. This user has a unique ID. This ID is sent to an auction house. So this auction house is also called an SSP, is in charge of finding someone to display an ad. Okay, so at least we do this. And after, so this house organizes the auction. We will see later how. So it sends this ID and all the context to someone who wants to display an ad, someone more or less smart, that can use some machine learning. So we do that also at it, in order to compute a price that this bidder is willing to pay to display the ad. And then the auction house will send back a win notice to tell the bidder, okay, you won, you can display your ad. So the next step is to generate the ad and to display it to the user. And after that, we will track the action made by the user, and the action that we want to track will depend on the fact that we are doing performance or branding. So if you are doing performance, we will track the conversions, the clicks, and everything. If we are doing branding, we will track the duration of the video that the user watched. Okay. So how does it work? Inside the auction house, so the user browses the internet, so you know that. And now the auction house will send what is called a bid request to a lot of bidders. So these are a lot of people of companies that want to display ad. They will all compute a price that they are willing to pay. Of course, the winner will be the one with the highest price. but the winner generally will not pay the price that he bid. Okay, he will pay another price. We will see what kind of price. Generally, it will be the second price, so it will be the second highest price, so the highest price of the competitors. Why? You have it an intuitive explanation. So imagine that you know as a bidder that if you win, you will win a true value from this ad. So it will generate a revenue for you that is called here a true value. So if you bid the true value, you know that you will pay less because you will pay the second price. So your profit will be your true value minus the second price. So the profit will be positive. So you're happy. If you bid less than your true value, it's the second case in the middle, you take the risk of losing the auction while you could have won it and paying the second price that was lower maybe than your true value. So the profit that you, this profit in red is a lost profit. You don't really lose money, but you could have won money. So it's not good neither for you. And finally, the last case is if you bid higher than your true value, you take the risk that the second price will be higher, so you will pay a higher cost than your true value. And in red, it's a pure loss. So in the second price auction, you are incentivized to bid with your true value. Okay, so now what is the true value? So in the branding example, actually, as a bidder at Teads, we will be paid by the advertiser only if the video is seen completely. They have like 15-second video to display, and they want to pay only when the video is seen completely. So there is a random event. We will be paid either a fixed amount of price, CPV, cost per view, if the video is watched, and zero otherwise. So the expectation of our revenue is the expectation of the CPV times 0 or 1, a random variable. So this expectation is the CPV, a fixed price, times the probability. So now you can imagine that we need to use some machine learning to compute this probability. Okay, so we have a lot of constraints. We use a lot of features with a lot of modalities because we have many advertisers, we have many websites, we have many user contexts and everything. We also have to train our model several times a day to keep them updated to the changes in the market, to integrate new campaigns and everything. And also, we have to be able to make a very big number of predictions every second, like 1 million per second. So we cannot use any kind of model because of that. And in particular, there is an article from Google, like 1 year ago, I think. Yes, they used a click data set from Criteo, another AdTech, French AdTech company. So which contained 40 days of click log. So they cut it in two parts, the first 33 to make the training, and the last day to make the validation. They used the opposite of the log likelihood as a metric, so the lower the better with this metric. And they compared 4 models. So basically the logistic regression against deep learning. So logistic regression with and without cross features, because logistic regression is a linear model, and to fight this issue, we cross the feature generally. So it improves the logistic regression, but it also increases the complexity of the algorithm. So you can see here the score. So the score is better and better. So when you use cross feature, you get a better score, but the prediction complexity, that is the most important for us, is increasing also. The complexity here is the number of multiplication you have to make. In the logistic regression, you make as many multiplication as the number of features, so it can go to 40 to 86 in this example. But with the deep learning, you have to make like more than 1 million multiplications. So okay, the results are a little bit better, but at a high cost, and also the training time is very long. So if you have to wait like more than a day before putting your model in production, it will be obsolete before going to production. So this is why we use, for all the real-time predictions, of course we do other kind of machine learning, but it's not the topic of the talk today. But for the real-time part, we use the logistic regression. So as a reminder, it's as simple as computing a scalar product. So it's very fast to use it in production.
Okay. Hello, guys. Hello, guys. My name is Han. And I'll start by talking about the motivations behind our stack, and then I'll go through the 3 major components: model training, model serving, and how we do experiments. Here in Teads, we are a very classic setup of machine learning. We have the offline model training, and we have the online model serving. And our online services, they make use of the models to do predictions, and in the same time to produce a different kind of logs. And this log, they will go through a data pipeline consisting of Kafka and Spark, and finally become our training log. And our model training job will take input of these training logs to produce a train model, and then train model then will be loaded into our online services to do prediction. Okay? It's a very classic setup and common setup. But here at Teads, we have our own challenges. The first one being the real-time prediction. As Cyrille has talked about, we are in the business of real-time bidding. So it means we only have 150 milliseconds of time for each incoming request before the auction times out. And during this time, we need to do a lot of things. For example, we need to gather the data for prediction. And then we need to evaluate multiple model predictions for each ad candidate for its final score. And then we need to do the ranking to select the best one to show to our clients. Just for some numbers, we have over 40,000 requests per second in our system. And that means we need to handle over 1 million model prediction scoring per second in our system. So it's not a small number, and it means that we need to make sure that the model scoring is as fast as possible, and also that the batch prediction will just not work in our case. Another thing is they want to do model serving outside of Spark, which means that our online code base will not depend on Spark. This is mainly for performance, and also the fact that Spark is very heavy dependency, which pulls Hadoop and other stuff, and we don't want to have that in our online code base. So basically, the model scoring should be very fast, and the model serving should be lightweight. Another challenge is that we want to have a full model improvement cycle supported in our stack. So it means that we want to be able to add features to our production model or change its parameters, and then we want to be able to evaluate all these changes by conducting an offline experiment. If the results are good, go online A/B test for some more realistic tests, and then go production if everything went well. So this will be the main workflow for our data scientists, and it should be reliable and also flexible to use. When we started our project nearly 3 years ago, we didn't find any framework or library on the market that can satisfy all our needs. Just take MLlib, for example. I believe the first thing is that its generalized linear model implementation has a limitation on the vector side. So we cannot use the very big sparse vector as the weight of our model. It's a kind of problem for us. And that the model serving MLlib would just need Spark as a dependency. So this is not what we want. So finally, we have decided to do it ourselves to implement our own stack with Scala and Spark. Now let's see a little bit more in detail, starting from model training. At Teads, we have different models in different teams for different use cases. So they may not have the same features. They may not have the same settings for model training. So an important part of our model training system is to make sure that each step of the model training would be configurable through a model training configuration object. And here in our stack, we implement this configuration as a class in Scala. It's serializable in JSON, and it's also one of the input of the model training job. Here we're showing you step by step our model training. On the left, you have the configuration part for each step. And what we show you is the JSON serialized form, and they are just part of the whole configuration object. At the beginning of the training, we'll use Spark to load the training log into a data frame. And the first step is to apply feature transformations onto this data frame. Feature transformations is just the process of generating new feature values by combining existing values. And new generated values would be added back to the data frame as a new column. One example of this kind of transformation would be the bucket type transformation, and you get one example on the left. You can see that in the configuration, we have input column name, the output column name, and also threshold for the bucket types. And basically, this transformation, it applies to a continuous variable and generate a new categorical variable depending on the threshold. Okay? And this is also a structure where our data scientists configure all the features for their models. The output of this part is still a data frame, but it has more columns because all the new added feature columns. And the next step would be just to vectorize all these values into a vector. So here in our stack, we support different methods. For example, we can use the hash vectorization, or we can use the classic one-hot encoding. And this method can be combined together to assemble a final vector. And if it's a supervised model, we also extract the label value here at this point. So on the left, you have the configuration, and we also have the column name for the label value here. And then the next stage would be just to train the model. Here in Teads, we have our own implementation for the model training, but here at this step, we can just very well use model training from MLlib or model training from the other machine learning framework, and they will just work. The output of the model training is a structure that we call a predictor. It's actually a structure that contains the trained model with all the parameters. And it is the structure that will be loaded into our online services by our model serving layer. On the left, you have the first part of the configuration for the model training. It is called an initial model. So basically, it is the starting point of the model training. So here in this example, you can see that in the model, we have an empty sparse vector. So it means that this model training would start from scratch, from a zero vector. And this structure, it also enables us to do what we call a model seeding. It is where a technique where the model training starts not from scratch, but from the result of the previous training. And this is a technique that we use in production to accelerate the model training process. And then we can have other settings for the training part. We can have the parameters for the optimization. We can have data of the regularization. And actually, we can have also specific components in the configuration depending on the model training type. All right? So basically, we can abstract model training in a function in Scala. It takes two parameters, the data frame, which is the log, and then a training configuration, and it returns a predictor which contains all the trained parameters. Things could get complicated when we have multiple models in production in different teams. So we need a very good way to manage all those models in production and also to deploy all those model training jobs. So here what we do in Teads is to assign a unique name tag for each model in production. So here you've got one example. We have information about team, about short description about the model, and then the date when the model is put into production. And the idea is that we use this name tag throughout the whole system at Teads to identify and to reference a model in production. And you get one example from our Scala API. Here is two functions. And the first function gets the training configuration by a given name tag. And the second function will load the latest training model by a given name tag. So you've got an idea how this name tag would be used. In our deployment stack, we use Scala code to define jobs. So here is a class for our model training jobs. And this class, it contains all the runtime parameters for our model training job. So you can see it has a model name tag to identify the model to train. And then it has information about scheduling, whether it's the daily training or it's an hourly training. And then it can have information about log to be used in this training. And then finally, we can even have some special Spark options to make this job run better in production. When we deploy this job, our deployment stack will just turn this class into a Jenkins job. And this Jenkins job knows everything to be able to launch the model training job inside an EMR cluster. And we also have integration between our scheduler with this Jenkins job. So the production runs of this job would be triggered and launched by our scheduler. But because it is still a Jenkins job, so we can always manually trigger and launch the job and override some of the parameters. So we can, for example, we can change a version of the library. We can add new option for Spark. So it's kind of very handy, this kind of manual runs for testing and for debugging. So you can see that it's really a flexible deployment mode. And finally, we have a dashboard for all the metrics that we have in model training. We keep track of things like training time, training set size, and also the model size to make sure that all the trainings are on the right track. Now that's pretty much for the training part. Now let's move on to the model serving part. Model serving is a layer that enables our online services to make use of the models. As I said before, model scaling should be very fast, and model serving should be lightweight. So this is why we have implemented this part as a library in Scala. And we choose a library rather than a prediction service. It's mainly for performance. And this, in this way, we can avoid doing HTTP calls. We can avoid sending the data across the network. It would be faster for the model scoring. And that a library generally has less impact on the online code base rather than a service. The main structure of the model serving is the predictor. It is the output of the model training job, and it's quite similar to a model training configuration. It's kind of like the configuration for the model scoring. And it is also a structure that is serializable in JSON, and you get one example on the right. And it contains 3 components: feature transformation, feature vectorization, and the train model with all the parameters. And we can see that the feature transformation and vectorization part is exactly the same structure that we have in the model training configuration. And actually, their content should be exactly the same for the same model between the predictor and the model training configuration. And in this way, we can guarantee that the feature vectors for the same model would be generated in exactly the same way online and offline, okay? Because the configurations are the same. Just one word about online feature transformation. What we do in the offline mode is that for each new generated feature values, we add it back to the data frame as a new column. But the problem is that in the online part, we don't have Spark. We don't have a data frame. So what we do is that we have created a structure called a prediction key. You have the sketch here. It's very similar to a row in Spark. And it contains a bunch of values and with a runtime schema. And we can add a new value into this structure with its type. So the idea is that we apply all the feature transformations onto this structure and generate all the new values and add these new values into this structure, rather than to apply feature transformations on a normal Scala class. So here is how it works. The model serving starts from loading the predictor into our online services. And normally the predictor is serialized in JSON on S3. And then once the predictor is loaded, we will generate a prediction function according to the content of the predictor. And this function it acts totally as a black box for the online code base. And this function just takes in a prediction data object in the form of a case class in Scala, and it returns a double as the score. It's a very simple function, so it's very easy to be integrated in our online code base. But what happens inside the function is that for each prediction data object, we will firstly cast it into a prediction key, and then we will apply feature transformations on this prediction key structure and generate all new feature values. And then we will vectorize all the values inside the prediction key into a vector. And finally, we apply the training model onto the vector to get the final score. Okay? So it seems like a quite complicated process inside the function, but actually we have very good performance according to monitoring with this kind of structure. Here maybe you'll see a little bit less on the left, but actually on average, a model prediction scoring, including all the steps inside the function, it takes about 55 microseconds in our production. So we can say that it's a very good performance for us. And now that's pretty much all for our production part. Now let's turn to the offline experiments, which is also the last part for our talk. The offline experiments is kind of like a cost-effective way for us to evaluate new models and new features. It is our primary tool to filter candidate models for online A/B tests, which can be very costly. So here at Teads, we have created an internal tool to simplify the process of creating and running this kind of experiments. And this tool helps us to formalize the testing protocol for all the experiments that we create. And it can keep track of the configuration and the result for each experiment, and it supports a wide range of metrics with an estimated confidence interval. Here's the execution of one experiment. The blue arrow here represents our data. and it can be viewed as a series of events happened in time. So there's a chronological order between the events. And this is why we always have our validation set, which is in green. We always have our validation set comes after the training set to make sure that this kind of order in time is respected during the execution. And for the same reason, we cannot use cross-validation here, because what can happen with cross-validation is that we may end up training the model on some later events, and we validate the model on some events in the past. So the result will not be correct because this kind of order between the events is not respected. And you can see that we also divided the execution into iterations. And for each iteration, the training set and validation set is shifted in time. And we do this mainly to simulate the fact that in production, a model will eventually be replaced by another model which is trained later in time. Okay? So the whole purpose here is really to let the experiment to mimic as much as possible the life cycle of a model in production to make the result more reliable for data scientists. So here's the UI. The main UI for our experiments is the notebook with our Scala API. We use Jupyter notebook in Teads with a Scala kernel called Jupyter Scala. And here, the step we are showing is the step of creation of one experiment. You can see that a lot of things are configurable to adapt to different use cases here in your company. We also do the analysis and visualization of the results inside a notebook with our Scala API. Here is the step we compare the result of two experiments inside the same graph, with the metric being the R square. And you can see we have the confidence interval on both sides of the metric line. For the last 18 months, we have over 3,000 experiments created in our company by different teams. And they run over a combined of nearly 500,000 hours of log. So it kind of shows that the importance of this kind of experiments for us. And that's pretty much all we have for today. And thank you very much.
Thank you. Thank you so much. We have time for a few more questions. If anybody wants to ask them, I'll come over.
Thanks for the talk. I just had a question on how do you scale out your prediction? So you'll have thousands of requests per second, right? So how do you sort of manage?
So basically, our online prediction, online services, they have many machines. So when a new model is available, and each machine will use our prediction, our model serving layer to load the predictor individually into the machine. So each machine have their own schedule of loading the new model, and then once the model is loaded, they will generate the prediction function to serve the incoming request. So the scaling should be just the number of the machines that we can have in the front end. Right.
And do you scale the number of machines by the load?
Yeah, so basically what we do, I'm not an expert on this part, but basically we put all the machines in an auto-scaling group. So they have rules and they scale up in function of the traffic.
Any more questions? I'm coming over.
Hey, thanks. I have a question about the model and the training in the search mode, like the search application. How do you deal with new companies that want to work with you as an advertiser, and how do you train them in your bidding system? Because it's a big issue. If you can elaborate.
So we don't do search. So we do mainly display and video, but we also have the problem of call start, obviously. So generally, we know at least the category of the advertiser. That can be a feature in the model. So it will work more or less well during the first hours, and we retrain the model very often And we also use exploration methods to deliver maybe the campaign, and maybe during the first hour it will be optimized fully. Yeah. But it's not an easy task. And for performance, it's even worse because the conversions are very rare. So.
Okay, that's all the time we have. Give it up for Han and Cyrille.